7.8, representations of equilibrium. Like it says here, 4 colored writing tools because your copies are black and white, so your diagrams are black and white. And so make sure you have 4. And so we can use particle diagrams to talk about equilibrium constant, or we could do vice versa. If I have the KEQ, I can draw a particle diagram, so it depends. And so we can do this qualitatively or quantitatively, depends on what the problem is giving to you. If it gives you values, obviously you're calculating something. If you're given visuals, then you're qualitatively doing something, so it depends. And so here's an example. This example, we're going to do 2 different questions. And so the first question is going to be, without doing any calculations, rank the systems in order of increasing Kc. And so here's our diagrams. And for the colorblind folk out there, I'll talk you through what these pictures look like. And so this first sphere is red, this second sphere is blue, this first sphere is green, this sphere is yellow, and then this sphere is blue, this sphere is red. I filled out the R part based off the diagram, so make sure to color these in based off the colors. So for the reactants, 4 of them are going to be red, and the rest are going to be blue. And then same goes for this is going to be green, the rest is yellow, and so on. And so even for the colorblind folk, you should be able to fill out this table based off me telling you and such. And so what you're going to do real quick is fill out this table based off what is given here. And so you're going to go ahead and do that. Which do you have more of? And then is KEQ more than, less than, and so on. So go ahead and try this out yourself. Pause the video. All right, ready? Here we go. So I have the values here. I talked about where there's more products versus reactants. As a reminder, we're using the ratio for K. So K equals products over reactants. And so if I have more products, it's going to be, K is going to be higher than 1. And if I have more reactants, then K is less than 1, and so on and so forth. Cool. And so we're going to go ahead and do the second part of this problem. So if the volume of the containers is 2.0 liters and each sphere represents 0.10 moles, calculate Kc for each of these systems. And so I'm going to do I, which is this first box here. And so for the reactants, I'm going to see that I have 4 spheres. And so 4 spheres times each sphere being 0.10, I got my moles of this substance. And then I have my liters, so I can calculate molarity by dividing the moles per liter. And so I get my answer here. And so I do the same thing for products. So products, I have 6 circles, and then each of them are 0.10 moles. And so I'm going to multiply those together to get my moles. I plug it into the molarity to get the concentration, and we got it. And so in order to calculate the Kc value, I'm going to put products divided by reactants. So I have 0.3 divided by 0.2, and I get 1.5. So that's one way of doing this quantitatively with numbers, if you're given numbers and you're giving a diagram. Cool. Now, I personally am not going to go through parts, scenario 2 and 3, because it's the same bloody thing. It's easy. Easy math. You got it, okay? Okay, second example. So here we have 10 molecules of XY together. So we're going to say the square is X and the circle is Y. And I'm also given the reaction here, and then I'm given my Kc value here. So we're going to sketch what it looks like at equilibrium. So rather than reactants to products, we're going to just sketch that out in general. So since I know that the Kc is 0.1, I can think of this as a ratio. So again, products over reactants. 0.1 divided by 1 is the same thing as 1 divided by 10. So approximately 1 out of every 10 reactants are going to turn into products. And so right now we have 10 particles of reactants. And so when I'm doing this, I realize that because I'm limited to 10, this ratio is not going to be perfect when I draw it, which is okay. It's based off whatever's given to you. Now, obviously, if the ratio works out perfectly, then do it perfectly. But because this one doesn't quite work perfectly, then we're not going to quite do that. And so if I'm going to draw this at equilibrium, this honestly would probably be like another box on the bottom, but I'm too lazy to do that. And so I'm just going to take this and like cross stuff out. So again, 1 out of every 10 reactants are going to become products. So products is X plus Y. So one of these is probably going to change. And so they're going to separate to X and Y. So here I have X plus Y, and so that's why they're separating. And so again, 1 product for every approximate 10 reactants. I have 9 drawn here, and that's it. Now, again, you don't want to make the ratio perfect if you're already given the diagram as such, because you don't want to mess with the law of conservation of mass. So mass cannot be created nor destroyed, and so that's why the ratio is not perfect, but that's okay for this example. Cool. Alrighty, here's a quick your turn. So we have our Kc value, we have our reaction, it's even telling you what you're starting with. So go ahead and draw this out before and after equilibrium. Alrighty, ready? Here we go. Boop, boop. So my Kc is products over reactants, so it's 2.00, so it's approximately 2 to 1 when we're making this. And so every 1 reactant, we're making 2 product, okay? So here's my before. So remember it said we started with 10 of each. So I'm going to say 1 diagram is 1 mole just for easy purposes. And so here it is. And so then I do my after. So my after is for every 1 reactant I'm having 2 products. So that's why these are together as my reactant AB, or sorry, my product AB. And then here's my reactant here. Now again, the ratio is not perfect because it's not 2 to 1. Perfectly, but again, we can't break the conservation of mass. So I have an extra reactant pair here that aren't combined, or I could have had an extra product not combined, or combined. Again, ratio is not perfect, so we just do the best that we can. Okay, that's honestly it for this section. So you should be able to draw stuff and then quantitatively do stuff with it if it gives you values, just like the first example. All right. Bye.